In the last few videos, we've talked about the 555 timer in bistable mode and astable mode. The last major mode to discuss is monostable mode. I'll explain what's going on here in a minute, but let's just hit the button for now so you can see what happens. So go and hit the button and see the output stays on for a certain duration. So when we push the button, the output stays on for a few seconds before turning off, and if we push the button multiple times like this, the output will still stand for the same amount of time. So on the value of the output, duration is controlled by the resistor and capacitor here. So the resistor, these two, resistor and capacitor, and I'll show you how to calculate that later. Alright, so to understand how the circuit works, a good place to start would be the data sheet for the 555 timer here. I have the LM555 timer data sheet here, and we can see on the first page here we have a schematic diagram of the insides. You can see it shows you all the individual transistors and stuff, but that's not going to help us very much. So let's look around for another diagram. So on the next page we see it shows us on the diagram here, but for understanding it, I don't really like how they did this because they matched it with the pins, but it's kind of hard to understand. So let's see if we can find another one. Oh yeah, they have another one here too. And this one's I don't like this one either. This one's too oversimplified, so I went ahead and made one. Here we go. Yeah, so I went ahead and made a schematic diagram that would be easy to understand and not too simplified, so here it is. So these are our peripheral circuits, and these are basically the internal schematic block diagram of the inside. So let's go ahead and break this down. We should first start label things. So we have 5 volts up here, and then we have 0 volts down here. And then over here on the side, I have 100k resistor. Right here I have a 10 microfarad capacitor. Then over here I have a 1k resistor, a 1k pull-up resistor, a push button here, and then of course I have an LED and a current limiting resistor for that, but I'm not going to show that in here. Now let's go ahead and take a look at the inside. So you can see here we have 3 resistors running down. Each of these resistors is a 5k resistor. I'm pretty sure it was just a coincidence that it's called a 555 timer and there's 3 5k resistors, but you know, it's for another time. So we have 3 resistors connected to 5 volts and 0 volts. So let's write these voltages down. So obviously this is the voltage divider. So at this point we're going to have about 3.3 volts. And at this point we're going to have about 1.6. Take a look at our peripheral circuits real quick. So we have a 1k pull-up resistor. If you don't know what a pull-up resistor is, basically we have a push button here connected to ground, and since our signal is going to be 0 volts, we're tying this high. So while this is not pressed, this is just tied high. And then when the push button's pressed, instead of going through this resistor, it'll go through here. So this will just be totally ignored. And then we'll talk about these two later, but these control the duration of the output. Let's take a look here. So this is everything's in its default state right now. If you guys don't know what comparators are, let me give you a brief overview. So comparator right here is this triangle with the plus and minus. Essentially, if you have a higher voltage at this positive side than a voltage at this negative side, the output will be positive. If you have a higher voltage at the negative side than the positive side, the output will be negative. And these both are the same thing here. And then this is a flip-flop or a latch. And if you apply a signal here, it'll set the latch by turning this output high. These are the 2 outputs, but we only need to worry about this for now. This is just the opposite of the output. This right here is a reset. If we apply a signal here, it'll reset the latch. So if we set the latch, then the output will be high, and then our output will be low here. If we reset it, this output will be high, and then this output will be low. Our LED is connected to the output here. So, alright, so let's take a look at what's happening in the default state. So we have 5 volts in here, right? Because we haven't pressed anything, which is higher 1.6 volts, which means this is just going to be a negative output, which means nothing's really happening. It's not setting the latch or anything, so nothing's really interesting happening here. Alright, so if our output is off right now, that means our not output is on. So let's follow this. Let's go up here. Oh, and then we have a discharge transistor right here. And so if our output is on, that means current is flowing through the transistor, you know, it's turning it on. And if we follow this, it goes up here. That means we have 5 volts directly shorting to ground, but we have resistor here, so it's not really shorting, but You know what I mean. It's going to ground here, and that's why we need a resistor, because of this step right here. It would just be showing to ground if we didn't have a resistor. So now it's going directly to ground, which means if we go down this line, this capacitor basically, this line is 0 volts. I mean, it's not charging up. So if we just were to draw it here, you can see that all the current's going from here into there, and any leftover current from here will be discharged through here too. We can go ahead and press the button. So when we press the button, you can see on this model the LED turns on for a certain amount of time before turning off. So we're about to press the button, right? We press the button. Now there's 0 volts flowing through here, right? Now it's not 5 volts, it's 0 volts. And 1.6 volts is obviously higher than 0 volts, which means we have an output of high. And now since the output is high, this sets the latch. When we set the latch, your output is high here, and this output is not high. So now our output is on, right? Now what keeps that output on? Well, so now we just turn this off, which means we turn this transistor off, which current is now not flowing through this transistor anymore. Now the only way for it to flow is down here. So current is flowing down here into this capacitor. So now this capacitor is charging up, right? And by the way, before this capacitor starts charging up, this was at 0 volts, which 0 volts is less than 3.3, so this was off too. So everything was off in default state. Now this capacitor is charging up, and eventually it will charge up to a certain voltage. Now when it charges up to 5 volts, as soon as it gets higher than 3.3 volts here, as the capacitor charges up slowly, suddenly it'll reset. We can see how this resistor and capacitor will control when this LED turns off, because that capacitor was charging up, and as soon as it passed 3.3 volts, be higher than this and have a positive output, meaning it would reset the latch. Therefore, output would be back to high again, which means that this resistor is now flowing to here, not charging up. Now this capacitor can now discharge just like that. So the capacitor just discharged, and the output obviously turned off. Just like that, and now everything is back to its default state, and that's essentially how it works. Alright, so I said I was going to talk about the equations, so I'm going to do that right now. It's really simple. It's just the time period, which would be how long the output would stay on, is equal to 1.1 times R1, which is just our resistor, and then C1, that would just be these two right here, R1, C1. And that's it. It's just multiplying 1.1 times. It's just essentially just multiplying the resistance and the capacitance together, and that would be your time period. You could easily go online and do some online calculators, and that'd probably be easier, but here's the paper version. So you could tinker around with these equations to get, milliseconds of time or seconds of time. So we're going to go ahead and calculate how long our LED stays on for. It looks like it stays on for like a second or two, but we're going to, finalize that. So for R1, we have a 100K resistor. And then for C1, we have a 10 microfarad capacitor. And we have to convert this to farads. And let's see, what would that be? And 10 microfarads and farads would be, let's see, we got 3, 2, there we go, yeah. It would be 0.000010. That would be what we actually use, and then we just keep this as ohms. 1.1 times R1, which would be 100,000, and then times our number here. Obviously I'm going to need a calculator for this. Where's my calculator?
One eternity later.
Here we go. After a few minutes of searching, I just found this calculator here. 0.1. If we multiplied correctly, it would have given us 0.11. And the time should be seconds. Well, that's obviously not right. Okay, I'll be back in a second. I think I did something wrong.
You fucking don't.
I see where I messed up here. This number is wrong. It's actually only 4 zeros, and then a 1. So that's a few off. Which would bring us to 1.1. So T about 1 second. And that seems about right. It's about 1 second, I would say. Yeah, so that would be their basic equation, and you could obviously tinker around with this. You could rearrange it to, if you want to find a resistance for, like, you already know your time period. You'd have your time, and you have 1.1. You can like, you can solve for different things here, and it'll give you a pretty accurate result. Alright, so we'll just take a quick look on the oscilloscope of what's going on. So have the purple lead hooked up to the capacitor, and the yellow lead here connected to the output. So if we go ahead and hit the button, here we can see our nice waveform here, and we can see our capacitor charging up. You can see, what is that one? Yeah, that's about 3.3 volts right there. So pretty much exactly when it reached 3.3 volts, dropped directly to 0, turned off. You can see our output too turned on, and we can actually measure the time. Yeah, there we go. Says it's about 1.3 seconds. So now if we continue this running, see how we can see signals there. And one thing I do want to mention real quick is if we hold the button, you can see our output never turns off. That's because, we're continuously connecting the capacitor to 5 volts, right? And so the output's never going to turn off, and then it'll just turn off because, see, by holding the button longer than the actual time, you're essentially it's just acting as a debouncer now. One last thing I want to go over real quick is, let's go ahead and get a nice signal. There we go, that's a good one. Stop it like right there. And if we go ahead and actually zoom in, and I've mentioned this in all my other 505 timer videos, but it's always worth going over again. If we actually zoom in here, you can see, oh, someone's texting me. See, we got a lot of noise here. And we got a lot of junk, unless that's all voltage spikes. So one thing you can do is by just adding a capacitor. I'm adding a small disc capacitor here. This is a 104, so what is that? A 0.1 megafarad capacitor. I'm just adding it across the power leads here. So now if we look at this, here, let's take a look at before, and let's take a look at an after. So you can see the before, and you can see the after. You can see it deletes a lot of the noise. And this mostly helps with the astable circuit. Not really much. You don't really need this for this very much, but no, that helps a lot. And generally, you want to be placing this decoupling capacitor as close to the 555 timer as possible, but it's just a breadboard here. Not all about efficiency. You only really need to do that if you were making a PCB or something. Anyways, guys, that'll end this video. And like always, all this information, parts and all circuit diagrams, all the stuff will be in the description. And if you have any, questions, let me know in the comments below. Stay tuned for more 555 timer content, because I'll have a lot more coming. PWM modulation, lots of practical circuits, lots of cool stuff. Even planning on making a coil gun or a Gauss gun, just using 555 timer timing. See if how practical is the 555 timer, stuff like that. Anyways, thanks for watching, and yeah, see you later.